Hello, this is a brief summary description of my 16-bit softcore processor written in VHDL. So it's my first big HDL project. I've previously played around with FPGAs and VHDL and incorporated designs in my retro computers. My previously built 6809 and 68000 machines include FPGAs to do things like glue logic, and the biggest previous piece of work I've done is a VGA controller, which this project now recycles. So it's a 16-bit processor through and through, so it has 16-bit address and data buses, 8 16-bit general purpose registers, 16-bit program counter, 16-bit instructions. It started off as only Word / 16-bit addressable memory, but I added a bus interface that can do byte accesses using either signed or zero extended access to present words to the rest of the processor. So it's a word that the ALU operates on, i.e. it's not like the 68,000, for instance, where it will where smaller quantities are truncated inside the ALU. There's no microcode. It's a coded state machine, just because I found that a more descriptive way to present what the control unit actually has to do with the various signals. So instructions, I won't go on about all of them, but it uses immediate values, and in this context immediate values are words that follow the instruction word, if you see what I mean. The load and store can operate on either they can even get the address for a register through an immediate value, or through a register with an immediate displacement, which is a pretty handy instruction to have, because it saves you doing ALU operations on addresses. It's a clear instruction, gives it a cycle quicker than an XOR. Status bits, 0, negative and carry if you had to implement overflow, which is useful for signed operations. The ALU is fairly extensive. It has currently defined 20 operations, all the usuals, plus byte swap, comparisons, bit tests. Yeah, that's probably about it, I think. So the ALU can either operate on a register, or rather can either use the operand from a register, or it can get the operand from an immediate. So there's an example: add register 0 with literal 1, 2, 3. So that requires 2 instruction words in the stream. So we've got conditional and unconditional branches and jumps, which basically get the flags to test from the instruction word. There's 3 bits, one that sets whether we're interested in that flag, and one that sets what that flag should be. And with that you can implement every permutation you would want. There's a NOP instruction, and of course, because every processor has a NOP, we have a hardware stack, so you can call a subroutine which pushes on the current program counter, and then return, which will pull off the program counter for the last subroutine, and push and pop, which work pretty much how you would expect them to if you've done any assembly programming. In terms of the stack pointers, with the push and pop instruction, that's set in the instruction code. So you would have push, the destination stack pointer, and the source the source register that you want to push. With call and return, that's also the case where the register to use is encoded in the instruction, but the assembler hard codes it for R7 out of convention, just because I don't want to set the stack pointer every time I call a subroutine. It's not particularly useful. So there's an example there. We've got loading a unsigned byte from the address held in the register in R0 into R1. So we have the 6 bits of opcode, the 2 bits of whether effectively the bus mode, in this case byte is set to 1 and signed is set to 0 to indicate unsigned, and the source and destination registers. So the implementation, I suppose this project really started from watching a few videos about how the MIPS processor worked, because it's a nice processor to understand because it's very well documented. It started off in academia, effectively was forked through academia, and the guys working on MIPS continued on, and the current version is called RISC-V, which I'm sure many people will be familiar with. And I watched some lectures on how the MIPS processor worked, and thought, that looks interesting, and might be something I can have a go at, tackling a project. I've always wanted to build my own processor, so I had all the information available. But this design does not use any code from MIPS or any other processor. But it borrows ideas, as everybody and everything does, from other projects. So there's a register file which holds the 8 general purpose registers, and at any moment 2 registers are continually having their value outputted to the ALU, and changes to the register file are clocked as you would expect. So you can either update a whole register, or you can do an increment or decrement operation on a register, which is used by the stacking. So in this context, increment and decrement is by 2, because that's the width of a stacked item. There's a program counter which can do the branch calculation itself, so it doesn't use the ALU. There's an instruction register that holds the current running instruction, and feeds out back to various places the various fields as shown there, and other ones into the places that need it. There's a fairly standard ALU design. It uses a 5-bit wide operation field, which is spread across 3 instructions. So that's one instruction is for the immediate mode of when you have an operand. The other one is for when the operand comes from a register, and the third variant is when you don't have a operand. So things like bitwise not, increment, and so on. They use a separate set of 16 ALU operations essentially, and that outputs the three different flags. Seem to be 4 flags, hopefully, when I implement overflow. So the bus interface component that does the munging between the processor's sort of native 16-bit view of the world and the outside world, which might consist of byte transfers. That also generates a bus signal on a bus error signal on unaligned word accesses. And you can know with this system where you've only got byte or word accesses, it's trivial to know when you have a bus error, because you're doing a not byte transfer, if you like. So you're doing a word transfer, and the low bit of the address is a 1. So that's illegal, because that would to get a result from that transfer, you'd have to do 2 memory operations and then combine the result. But the processor doesn't do that. There's the control entity, which handles all of the state processing for each of the instructions, and generates all of the control signals used by the other elements. It also controls some muxes which are used to divert buses around in the sort of outer layer of the processor. So, for instance, the word being outputted at any time can either be from the register file, or it could be from the ALU. I think I'd have to think that through. It's been a while since I looked at the code for this project. But basically muxes are used to route the buses between the different elements. So then there's a top level that I've just touched on there, also known as a data path, and there's a little bit about muxes. So yeah, it's a call jump that can also set the address. That's when you're calling a subroutine and you need to write the current program counter into memory. So it's currently using 1,000 roughly logic elements on a Cyclone 4. So it'll fit in any FPGA more or less made within the last 20 years. So I'm using the custom ASM retargetable assembler. This is a very, very nice project for anybody who is building their own processor. I can't recommend it enough for people tinkering with projects like this, or people building processors on breadboard. You basically define your instructions and the byte sequences that are required to represent them, and it, you can feed it an assembly program. It's very cool. In this case, for instance, you can see individual instructions there, like inc. That's a single entry in the definition or rather there is a single entry for each of the system level opcodes. So in the case of ALU operations, there are 3 as I described, and then you have a separate list of operations for the ALU. And well, the long and the short of it is the entire definition for this processor inside custom ASM is I think maybe 20 lines of description in its declarative syntax, and it's very, very easy to use. It does have one quirk which affects me at the moment, which is that it's not really geared up for having an instruction width different from the addressable element or the addressable memory width. So in this CPU's case, the instruction width is 16 bits and the addressable memory size is 8 bits. So I have to do a bit of kludging around custom ASM to get that to work. But it's a minor detail really. Go and look at custom ASM if you're interested in this stuff. It's very cool. So my test bed, which I've showed in a video where I'm playing my Snake game, is a DE2115 board. It has many peripherals. It's got sound using, I can't remember the part name, but basically a codec driven by I2C, VGA. It's got for some reason dual gigabit Ethernet. It's got a DB9 serial interface. It's got endless buttons and LEDs. It's got a 2-row 16 column, I think, LCD screen. It's very, very nice. It's rather expensive. I think it was about £500 from Mouser. It's also borderline obsolete. It's about 10 years old, I think, the design, but it's very, very nice for this kind of thing. Many of the newer boards have hard processors, or they're hard processor FPGA combos, and I wasn't really interested in that kind of board. But this design would work on anything, any FPGA pretty much that has a PS2, if you want that particular peripheral, and VGA. But yes, you could embed it anywhere. So I'm currently in my Snake example that you might have seen. It's got 16 kilowords of dual-ported memory for the program and the video, which is very, very easy to use. So you have a reader basically reading the memory on one side, and then the CPU is accessing the other side to do reads and writes. So easy peasy. So there's a few things I'd like to do. Some of these in the short term, some of these a bit further away maybe, depending on how much time I get to work on this project. I want to tidy up the use of flags. I need to add an overflow flag. That should be very easy to do. I need a test bench for the controller. I've currently got test benches for the register file, the ALU. I think that's it actually. um, so I need to write a few more test benches because they're very useful to do. They're very useful to have, and they make you can then make changes to things with more confidence. A few more instruction ideas I've got is PC relative addressing, so you can load or store to memory relative to the current program counter for position independent code. Barrel shifter might be fun. I've always wanted to have a go at implementing one of those. Multiply and divide. Certainly this size Cyclone 4 has a multiply unit inside, which I've never done anything with. And it may be useful to restrict ALU operations to byte-wide quantities. I noticed, for instance, on my snake game, the cyclical buffers that hold the row and the column for the snake's position are 256 bytes long, but when I increment to move along the buffer, I have to mask it out with FF hex to stop it overflowing the 256 elements. Whereas if I could, in my increment operation, tell it that I'm manipulating a byte quantity, then the ALU itself would contain the value. So that might be something to do. Not sure. It kind of dirties the design a little bit, so I may not do it. Interrupts should be fairly easy to do on a processor like this because there's no pipeline to worry about. It's just a test to do in the fetch instruction, and I could either insert a jump or directly manipulate the program counter. Ideally, it should get a vector address out of memory and then jump to that. But we'll see. But, interrupts will be good. And software-wise, the next thing I'll write, I've kind of I have half started it. It's a machine code monitor. It's a nice way to play with the hardware I implement, and I could then, if I wanted to, extend it to be able to do things like load code from the serial port, and then run it without having to effectively recompile the entire design and then send it over the JTAG port. Which I think the cycle to get a new design on at the moment is probably about 2 or 3 minutes, which is a little bit too long for my liking. I'd like to just be able to press a button and see it run new assembly code if I'm not actually changing the programmable logic in the system. So yeah, that's where I am now. It's been a lot of fun. I may carry on with this for a few more weeks or even months, but at some point I'll be getting back to my 68,000 project because I really want to finish that board, and maybe show everyone what that can do as well. Anyway, thank